So I was learning distributed deep learning in PyTorch today. Basically, torch.distributed package. Torch.distributed is basically a package which allows you to train your deep learning models without writing much code for any kind of distributed computing and all. So there are different libraries and frameworks like PyTorch Lightning, which allows to train your models with distributed computing without modifying any code. So why would you learn this torch distributed when you have this library which do all these things with in out of the box? Suppose you have to create your own library and do some modifications, then it is really a nice skill to have. So how would you learn distributed deep learning? So I am here to give an overview on different components of distributed PyTorch distributed package. So let's get started. I have pasted few of the references here that I have used in this video. You can find these links in the description. So let's get started. What is world and rank? Explain world. Let's suppose that I have two servers and four GPUs on each of the server. Okay. So suppose if one server has 4 GPU, server 2, server 2, 4 GPU. And if I have to train a model, then what I will do is I will create 4 processes on this server and 4 processes on this server. Each of the 4 processes will use each of the 4 GPUs. Now, in each of the server, I have 4 processes, and in total I have 2 into 4, that is 8 processes. This is my world size, and I have 8 processes. This is basically, I will create a group of process, and I have a group in which I have 8 processes, and this group of processes is called world. I have a world, and in this world I have total of 8 processes. Now what is rank? So since I have a total of 8 processes, or you can say I have a world size of 8, then the rank here are 0, 1, 2, 3, 4, 5, 6, 7 to 8. Sorry, only to 7. Now, since I have 8 processes, how do I identify each of the process uniquely? Rank is basically an unique ID given to each of the process to uniquely identify them. So I will say this is my rank 0, rank 1, 2, 3, 4, 5, 6, and 7. So rank is nothing but just a unique ID which can identify a process uniquely. Now what is a local rank? Now if you see, I have one group and one group has two servers. Now inside one server I have 4 GPUs. So I can say that if I create a local rank, then each of the GPU I have 4 process. Basically the local rank can be for GPU 1, 2, 3 and 4, 0, 1, 2, 3. Now I know about what is world and rank. So you can read here. In distributed computing, you have a group which contains all the processes. A world is that group, and the number of processes in a world is called world size. So what is a world rank in a world? Rank is a unique ID given to a process in the group to uniquely identify a particular process. Now communication methods. Let's go to PyTorch distributed overview and see what are the different communication methods. What is point-to-point communication? A transfer of data from a process to another process is called point-to-point communication. Basically, you have four processes, and from one process, you can send the data to a different single process, and you can receive data from a different process. Basically, the data transfer is from one node to one process to another process. Data transfer are achieved through two methods: send and receive. The send and receive method are two versions. One is asynchronous and another one is asynchronous. And then asynchronous is starts with I. So collective communication, there are multiple ways: scatter, gather, reduce, all reduce, broadcast, and all gather. So in scatter, you can see that from one rank or one process, the data is transferred to all the other processes, and in is just opposite of scatter. In scatter, the data is received by one process from all the other processes. Reduce receives data from all the processes, and it reduces it using operation, maybe summation or multiplication. The difference between reduce and all reduce is only one node is accepting the data from all the different processes, but in reduce all the processes receives data from all the other processes, and it reduces it using an operation, maybe summation or multiplication. Broadcast and all gather. Broadcast, basically, one process sends the data to all the other processes, and all gather is just like broadcast. Just the difference is all the processes send the data to every other process. Basically, process 0 will receive data from process 0 to process 3, and process 1 will receive data from process 0 to process 3. So all in the ending, all the processes will have data from every other process, including itself. As opposed to point communication, collective allows for communication pattern across all the processes in a group. So basically, you just saw that in point to point, only one process can communicate with another process, but in a collective communication, one process can communicate with multiple processes at the same time. A group is a subset of all our processes. A group is a subset of all our processes that I just told you when I was explaining world and rank. So a group is also called as world. To create a group, we can pass a list of ranks to this.new group. By default, collectives are executed on all the processes, also known as the world. For example, in order to obtain the sum of all the tensor of all processes, we can use this dot all reduce tensor, OP, and group collective. Basically, it wants to say that if you create a world with suppose two groups here, 0 and 1, a group of two, and you have a tensor and you want to sum the tensor from both the processes. So you can use this dot all reduce, you can pass the tensor, then what you will do is you will torch.distribution has this reduce operation, summation, multiplication, here some product, max and min. So you can pass the operation which you want to perform on the tensor, and you can pass the group, and it will do the all reduce operation on your data. Now that I have talked about the terminologies of distributed deep learning training, PyTorch, let's talk how does the model train on it in a distributed fashion. Suppose if I have a model and I want to train it on two servers with 1 GPU each. What happens is the model will be copied on GPU 1 and GPU 2. And if I want to train my model on a data set with a batch size of 32, then this 32 will be divided into 16 and 16 for each GPU1, and it will be sent to GPU1 and GPU2. Basically, my data GPU1, GPU2, model replica, model, compute the gradients. Basically, what happens is the data is copied to GPU1 and GPU2, and the data is passed through the model replica on both the GPU. Now the gradient is calculated, and this gradient is then synced and updated. There are multiple ways to update the gradients. This article by Save Anal describes the methods very easily. So we have synchronous and asynchronous distributed SGD. In the synchronous SGD, what we do is we copy our model to each of the GPU, and we pass our data to each of the replica. So basically we call the copied model on each of the repeat GPU a replica. So we pass our data to each of the replica, and we calculate the gradients, and we and in order to update the gradient, we average the gradients in all the nodes or all the processes, and then update the gradient. So if you see the algorithm here, get a mini batch, then compute the gradient on local. So by local you mean in on each of the processes. Then in the fourth step, get the gradient from all the four processes, or get the gradient from all the processes and average it. Then use the average gradient to update the model. This was synchronous SGD. Now let's talk about the second one, asynchronous SGD. The asynchronous setting is slightly more interesting from a mathematical perspective and slightly trickier to implement in practice. Each replica will now access a shared memory space where the global parameter WTG are stored. After copying the parameters in a local memory, it will compute the gradient and update the weight with respect to its current weight. The final step is to apply gradients to the global parameter in the shared memory. Basically, what it wants to say is get a mini batch, then the model is copied into all the local processes, and we maintain a global model weights. Then we pass our data on each of the local models and compute the gradient. Now we will update the gradient separately for each of the gradient obtained from different processes without synchronizing with other processes. So if I have three processes here, so I have three local replica, and in the second replica we are updating the weights, then we won't care if the first and the third is updated or not. So we don't have to wait for the other replicas to finish the work first. This creates a problem of staleness. This creates a problem. Suppose model 1 and model 3, or replica 1 or replica 3, have a weight from step 1, but the replica 2 has updated the weights before they could update the gradients. So the first replica and the third replica will have older weights. This creates a problem of staleness. So what we do is we divide the gradients by their staleness. So this limits the impact of staleness. So that's all from me. Hope you learned something new. With that note, bye bye, take care.